Hello everyone, my name is RUNHANG ZHANG. I am a financial technology with data science MSc student, and my supervisor is Professor John Cartledge. The title of my final dissertation is Exploration of Task Classification in Federated Learning for Commercial Product Categorization. Let's get started now. First, let me introduce the background information of the project. Spend analysis is an essential tool for a company to save costs. For example, Tesco needs to buy millions of envelopes each year to meet customers' communication needs. Small items, such as envelopes, are often purchased only when they are required. However, the price of envelopes varies from time to time. It saves tens of thousands of pounds from buying millions of envelopes at a lower price, even if this price fluctuates by only 2 to 3 cents. In spend analysis, product categorization is a very important step. However, classification is done manually now, which is slow and extremely costly. Therefore, an automatic product categorization system is in desperate need. This project worked with Clariton, a small to medium-sized enterprise based in UK, who specializing in procurement automation and spend analysis, to implement a distributed product categorization system in federated learning to save labor costs and increase customers' rapport. The research outline starts with implementing product categorization methods in natural language processing in WDC 2020, which is an open source dataset. Because Claritom's data is restricted and the WDC 2020 data is larger and noted. Since both datasets are essentially task classification problems that classify products based on their description, the findings can be transferred from one to another. The core model in this project is BERT-based pre-trained models. It is a pre-trained model proposed by Google AI Research in 2018 and have very great performance in other task classification tasks. First, the model is used in a centralized way, which means training process is only finished in a single model in the open source dataset. Then, it is migrated to federated learning to create a distributed system, and their performance is compared and analysis. Finally, they are applied into Clariton data to find the final classification results. This part is about the machine learning method used in this paper. First is about traditional machine learning methods, including k-nearest neighbors, naive Bayes, and convolutional neural networks. They serve as the benchmark models in this project, since they have adequate performance in other task classification tasks. The advanced deep learning methods, as well as the core model in this paper, is BERT-based pre-trained models. As you can see in the following figure, the model comprises input layer, preprocessing layer, BERT encode layer, dropout layer, and softmax layer. In this instance, the input layer takes inputs of type string. BERT's preprocessing layer preprocesses the input irregular strings to uniformly formatted data streams. The preprocessing output is given to the BERT encoding layer to produce encoding results. Then the dropout layer is intended to prevent overfitting and enhance the model's performance on the validation set. Softmax layer is used to produce the final result as a probability distribution of samples belonging to each category, with the class having the most significant probability being the forecast result. Since the complete BERT model is too large, in 2019, Sun and his colleagues proposed 24 compressed versions of BERT in their paper. This project also tests the performance of the small BERT model with only two hidden layers. Next is about the federated learning process. The architecture used in this project is client-server pattern. In a client-server architecture, K clients with the same data format cooperate with the server to build machine learning models. Then, each client sends the weights to the aggregation server. Weights refers to the value of the parameters of each layer in deep learning models. The server then applies aggregation methods, such as weighted averaging, to the sent weights. After processing, the server delivers each participant the aggregate weights. Each participant modifies the parameters of their models based on the returned results. After finishing all these processes, it concludes one training round. It should be noted that the deep learning models in each client and server are centralized BERT models with the same structure to ensure that the weights can be transmitted. The training process will continue until the loss of the server model converges. This part is about the experiments in the open source dataset. First, it is about the analysis of the training process. The following figure shows the loss and accuracy changes of the complete BERT model as well as the compressed BERT model in centralized and federated ways. The right figure shows the process in federated learning. Compared with the left one, the usage of federated learning leads to about 0.5 increase in loss and a slight decrease in accuracies for about 0.05. In both figures, the usage of the compressed BERT model leads to a dramatic drop in model's performance. An interesting phenomenon occurs when using federated learning. The loss and accuracies are subjected to a slight linear variation. It may be caused by the weights transferring process in federated learning, since the server needs to synchronize with the client's weights when coveraging. In this section, I explore the effect of varying number of classes in the dataset. The top 5, 10, 15, 20 amount of project type is chosen. It should be noted that the reduction of categories in this dataset for this experiment leads to a corresponding change in the size of the dataset, which may also lead to the phenomenon in the diagram. In this figure, the gap in classification accuracy between centralized and federated learning decreases when the number of classes becomes smaller. There are two possible reasons for the occurrence of this phenomenon. The first is that as the number of categories is reduced, the likelihood of misclassification lowers. The second is that data distributed among different clients may be pure, which implies that a much more significant proportion of samples will fall under the same category. What's more, it is obvious that using compressed BERT leads to a reduction of approximately 20%. This part is about experiment in Clariton data. As you can see, applying models in federated learning leads to a very small decrease in models' weights average Epworth score, for about 2%. In Kuna's paper, he also demonstrated that using federated learning may lead to a slight reduction in models' performance, which support our result and can also be found in the test with the open source data. On comparing the different algorithms in the Clariton data, it is obvious that the BERT model in this paper outperforms others dramatically. It should be noted that hierarchical classification methods is used by Yuting in 2019 with the same dataset, who was working with Clariton with the same issue before. However, the centralized BERT and the federated BERT outperform his methods for 0.06 and 0.04 respectively. As feedback from Clariton, they have not only been provided a model with a significant performance enhancement, but has also converted this model to federated learning, enabling Clariton to use and enhance its own system. Therefore, this project has been a fundamental success. Thanks for watching.